come back again. So we want to start the journey now. So far, we have been looking at some prerequisites of machine learning. Those are the prerequisites so far, which means that the basics of what we need to learn before we go into machine learning proper. So now I want to start looking at machine learning step by step. So today I just want to give us a general overview to prepare us to the journey of machine learning. So you must understand that the purpose is to transform data for optimal performance, optimal model performance. So for Scikit-learn, that's a API overview which consists of 3 interfaces. The first one is called estimators. In the estimators, you to estimate actually the parameters. The first parameters are the features. The features you want to fit into the model, and the target variable that you want to output. So these are what the model will learn, called learn model parameters. So the X here standing for the features, whether 1, whether 2, 3, 4, 5, 20, doesn't matter number of features. Here we have our single value called target variable. All right. So this is concept of supervised learning now. Okay, I'm just using that one as example to describe. So later we go into the major one. So all models such as linear regression, forest, all of them fall to the same categories. So you are going to be seeing them consistently like that. We also have what we call transformers. This one transforms, most importantly, scaling of features. I've shown us examples how you can transform your data, okay, in different ways. Okay, there are more other ways by which data can be transformed, but at least those few ones we have dealt with, I think they are okay for now. So we have normalization, standardization, and so on. So we also have PCA type also. So we also have what we call predictors. So after our data has been fitting into the respective parameters of features and the target, then we transform if there is a need to, then we now predict. Okay, in the predict section, we do what they call training and testing, right? We do training and we do testing. So we make predictions, which include classifying or classifiers and regressors. So don't forget, we have two now. We have a classification and regression. Don't forget that. So we're going to be looking at a regression first in the next class. We start with regression, then go into classifications. So, but today I just want to use this classification concept to generally explain do some overview of machine learning. Now, going to the splitting our data into 2. Let's use our usual data set for now to to do a illustration or to demonstrate what I'm talking about. So we load our data set here called erase. So click on load to see the first 5 lines. We run this line. So we see the first 5 lines. So don't forget, it starts from 0. I've said that several times. So this is our target variable called species, right? So now we have only 1, 2, 3, 4 features here and 1 target variable. So don't forget. Okay, so that represents X. This one represents X. That 4 features now represent X. Y. This one represents Y. All right, in the fitting parameters. Okay, so when we say testing, training and testing, we are looking at splitting the data into 2 categories, one for training, one for testing. So most times we use different percentages to do this. This is foundation of model evaluation, right? The first thing we need to call is in our Scikit-learn is to call this model selection and import training test split. So this is very important. Without calling this, you cannot do anything. So we have to import this library, training test split. So the purpose is to help us separate the data into training and testing split. So we have features called x separated from target variable y. So when we call our x, it say equals to our data set is called erase. Just for now, we use a raw data set now for now. No scaling for now, this thing for now. Just use the raw one just to show example. So we have erase.drop. What that means, I want to drop this data set called species because it's number one, it's our target variable. Number two, it's not a number based column. So you can drop any column easily when the column is not a number based. Okay, the axis is just one. So we are going to drop it because we are using it as our target variable. Okay, so we drop it now. We have now, which means in x now we have what you have remains is just 1, 2, 3, 4. Okay, from this erase we have dropped 1, which is the last one here. Okay, so you can also drop in many ways, but like this, let me just show you this example. You can drop using your NP concept. You know what I mean by NP, NumPy, using matrices form. So just mention the column numbers instead of using the name of the data set. I mean, name of the columns rather. So our target variable is y now, which is called, we are going to use erase. Call our species here, which one here, we call it a, assign it to y. So now we have our two set of data ready. These two are very important so that we can proceed. Now, in this case now, for this particular set of data, we want to now split them into two. So the second type of splitting now to two. So most times 80 to 20% is most acceptable, commonly used. Though you can at least try to modify a little bit. It depends on your data. Okay, here if you have a small data, 80 and 20% is okay. So you can use 70 to 30, you can use 25 to 75, depends on your data. So just have to check and see when you run several times, you will see that the data that is balanced for your model. So we call this particular features x-train, x-test, y-train, y-test equals to, we assign it to our this particular library we call here function here, train test split. So we pass our parameter x, y to it. So we have more other parameter we are put to pass. There are so many parameters surely, but we have just few ones because we're going to be using random forest later to do the illustration for now. So we have test size, which is 0.2. What 0.2 means 20%. That's what it means, 20%. So if I want to use 30%, I just say 0.3, which means the rest, for the test size now, the rest will go for training. That's what it means. I'm saying that 80% should go for training, while 20% go for testing. That's what I'm saying now here. So I use random state equals 42. This is for reproducibility, which means if I supply this now, I can run this particular code on another machine to give me the same result. Why? Because I use a random state equal to 42. If I change it now here, if I change it over there on another machine to give me a different result, can be randomized, randomly modified. Okay, so but just make sure that they remain the same number. All right. So here we have 42, just to make sure that when we take it to another machine, we have the same result exactly. That's what it means. So we call our stratify equals to y, which is preserve class distribution. Our class is y. Don't forget. So these are our target variables. We have 3 classes there. Okay, which means that Sentosa, Phagenic, and the third one. So we have 3. So it preserve the class distribution because now we are not dealing with imbalanced data for now. All right, we're just starting introductorily. All right, so now we can print out this and see the shape of this data x training one and testing one. Can see the shape. All right, let's print and see the shape. Right, so here training set shape equals to 120 by 4, then testing is equal to 30 by 4. So if you look at it now, you can see the percentage of training is 20% of this. All right, so and this is 80%. So that is what we have done so far. All right, 20% to 80%. So we have 120 here. We have 30. Total 2 is actually 150. Right, so we have splitted We have split the data now. So we are looking at a class, this one class distribution for the target variable now for each one, Sentosa, Virginica, and Ferris color. So this is how they are distributed. Right, in this now, why split data? Number one, models need features. So this is which is X now in quotes, and target Y separately. They must be separate. So that is first thing you must understand. You must separate your features from your target variable, which is Y. Right? It prevents data leakage where test set influences training, because most times the test set always influences the training. So data may be leaking when it's too lopsided, right? Yeah, there are more to this side than this side. So we simulate real-world example performance on unseen data, because the purpose of testing so that it can help us to simulate unseen data on the model. After the training, we need to pass in data to test our model using unseen data. That is the purpose of that small number we separated, because model have not seen that before. That 20%, yes, that's what it implies. So we are now supplying that 20% to test our data to see how the model works, how effective the model is. All right, we evaluate model performance on unseen data. Also, 80 to 20% is a common for all data sets. It's common. All right, you can explore more on that. Stratification ensure each class that we have now appears in same proportion in both sets. That's the purpose of stratification. Let's stratify. Why? Don't forget we did that. So you're able to split them separately, because for now we are not dealing with imbalanced data. Okay, they are all the same. So we have it's critical for imbalanced data set. Okay, it can help us to undo that area. So random state makes split reproducible for comparison, which I've explained now. All right. Now let's do the model training first. All right, before we do the testing. So we're using a random forest now as an illustration to do the training. Now let's call our new library called Scikit-learn.assemble. So under this particular one, we import random forest from here, from this assemble, random forest classifier. Okay, that's what we need for now, because we are dealing with a random forest now. So if you are dealing with maybe SPM, we import different thing. I'm going to neural network, we import another thing here. So this one changes based on what we are bringing in. All right. Now let us initialize model with key parameters. Now let's create a random forest model. Call it rf_model. Call our model parameter here, model function here. Okay, random forest classifier. We call it now. We're passing our parameters here. So n estimators, this number of decision trees. Because don't forget, the concept of random forest is to create decision trees, right? So help us to handle that area appropriately. So the maximum depth is 3. That's each controls the tree complexity, because tree can be complex most times. So we want to control it, not to be too complex. Then, because we can possibly print out the tree out later if you want, which we don't need that for now. So random state 42 for which we are assured just now. Now let us train the model now. We are passing our model. Don't forget this rf.fit. That's what we did last. I will show you up there the other time. You fit in your x and y. So our current x and y are S train and Y train, because we have assigned S train to S train. I'm breaking them down, Y to Y train. So we are training X and Y now. This is called features, and this is called targets. Okay. If you look up here, you will see that the S train here has been assigned. Okay, because what you are saying that you are saying that this S go for S train, this Y go for Y train. That's what you are saying. But that's what this particular splitting understand. You understand that your X is your S train, your Y is your Y train. So it takes your X as your S train and your Y as your Y train. So that's why you call this function, and you're passing X and Y into it, then other parameters. So let's move on. Now we are calling the training to train now. If you run this code now, it will train for us. Then we can check the model importance in case you want to change some things. This is not necessary anyway, but just for you, in case you are running into trouble, you can Google run this line of code also to see which columns or possibly features are not needed that you can drop. Okay, so if you run this code now, to give you feature importance here, which means better length is higher than all of them, then followed by better width, all right, then followed by separ length. Separ width is very poor, so in some cases you may need to drop this, all right. But for now, let's just go ahead and continue. We are not dropping anything for now. We don't need that, it's not necessary. Okay, so but I'm just showing you in case you are dealing with data set, you can run this line of code to see which one needs to be dropped. Okay, so why random forest actually? It handles nonlinear relationship well, okay, and built-in features importance. Because this importance we just run now, it is built in together with random forest. We didn't run it, we don't create the code specially like the one we did last time. We created a special code to run that. We even use ANOVA method. But this time around, we just call the function pd.series from random forest. We're passing our model into it, and we call feature importance, and it runs for us. So it gives us the our importance feature. So we also make it ascending order of importance. All right. So you can see it's very easy. Okay. Resistant to overfitting through ensemble learning. So it's resistant to overfitting, not allow the data to be overfitted. And it has some key parameters such as n estimators, which I've explained up there. More tree increase stability but slow training. Okay, so the more tree you have, the more stability you have in your training, but this training will be slow but better. The max depth limits tree growth to prevent overfitting. Okay, so we have feature importance, which I just showed now, which feature most influence predictions and help validate our earlier feature selections. So we can do that earlier before we go further, so that if anything, we need to calculate, check, and remove or hide. Now, let us test the model now. That is called evaluation of the model. It simply means testing the model. It's as simple as that. So don't mind those terminologies. That's just what it just means. So we call again our sklearn metrics. Now, because we are testing now, so we are evaluating. So we need to use metrics now to see our results. So the metrics we have to import, want to use accuracy score, want to use confusion matrix, want to use classification reports, and they want to see ROC AUC score. So there are more under the model evaluation that you can see, but I just want to see few ones. So you can still put comma and add more based on what you want to see from your metrics, right? So if you run this line of code now, we can generate now our Y prediction. Now we assign it to our RF model, which we have created. Our model of is for RF model dot predict. Don't forget to predict. We pass our X test, which is our features. Okay, so we don't need this line actually. Normally, under normal circumstances, I only run it because I want to see ROC score. If not, I don't need this line. Okay, you can eliminate this line in case you don't need to see ROC score. But if you want to see ROC score, you need probability. So it's very important. That is what you're able to split that and give you the result. So we are on this line now. So it has been run. Nothing is showing because we are not printing anything yet. So we are going to print output here in the next line. So by calculating our metrics. So our metrics already inbuilt calculated because we have called all these parameters. Okay, what you just need to pass into them is that they pass your feature, your X and your Y, your S test and Y test. So you just pass them. You can see Y test, S test, pass as a parameter into it, and it will give you the result automatically. So here let's say we want to calculate, we want to print our string. This means a new line, next line. So accuracy score, we call this function from our libraries we have brought in, Y test, comma, Y prediction. So we pass in the, so again, your confusion matrix, we call it again, we pass the same thing in. All right, so these two is very important. We need them, and we also need our calculation report. If you want the calculation report, you can also print it out in details. So which means we pass the same thing inside. You can see it's so easy, so simple. Just follow the same concept, passing this, the same thing you repeat for this, you repeat for this, you just passing the same thing, and you get your result out. So don't forget, you are going to have a diagonal-based result. The diagonals show correct predictions. Okay, that right. Off diagonal shows misclassification, which I'm going to see very soon. Though we don't really need this, but I just want to understand this for now. In the later time, we are going to be dealing with it later. Okay, so ROC one versus rest, we print our score out, ROC score, Y test now here. But instead of now printing our Y prediction here, we call our probability here, which I showed you just now here. Why we use this guy to print our probability out, our ROC out. So we call it here. So multi-class equals to OVR, means 1 versus rest. Now I'm going to explain what that means shortly. Okay, so but let's run this line of code now and see the result. You can see the result here. Control matrix here. Okay, we have a actual value, we have predicted value, we have actual value here. So predicted up here, actual this side. So you can see here diagonal here 10, 9, 10. These are diagonals. These are the correct prediction. And this off diagonal 0, 0, 0 here, 1, 0, 0 here. These are off diagonals. Okay. So now you can see the port here. Show the port. Precision recall F1 score support. All right. This is our ROC accuracy. The mean accuracy is 96.67%, or you can just say 97% approximately. Okay. That's our accuracy. Our ROC is 98.66 or 67 rather. So now, based on this now, we can also, maybe most times we may need our result here in 4 decimal values. Sometimes you see this one like this all the time. But a lot of you want them because you may want to benchmark a paper, for example, and you have having 95. This means 95% now, and that but this is not the exact values. Yes, these are the exact values. You still have more values as it's hidden. So if you print complete value out in 4 decimal values, you will see that you have some points that is not showing. You show it at 95% straight. But the answer may be 95.9.45, for example, or 66. So that 1.66 is very important because it's enough to benchmark a paper. Okay, so you can just use you put comma here, just put comma here, and say digit equals to 4. Okay, it's as simple as that. So simple. So in this case now, when you run this code again, it's going to give you this one in 4 decimal values. So you can now see the major results. But this one you are seeing one here, they're just a rounded off values. They are not really the real figure. Sometimes the figure might be 99.98 sometimes, okay, or 99.99. So just see 1. Sometimes you may not need 1. Maybe 1 is too, maybe it's so high for you. You want 99 point something. So you have to use your 4 digits here. So let me run this again and see what I'm talking about. You can see now. See, this is called 94.74. Can you see? So you already ran it up for us, which you don't want. So you want the exact values. So you have 95.24, 96.67. You can see them here. So that is what you need. So it's very important. So now I will just explain now the concept of a OVR. Okay, it's a strategy for extending binary classification metrics to multi-class problems. Okay, in our case we have 3 classes now. Okay, in our species. So how it works is that for each class, okay, the problem is treated as one class versus all other classes. Maybe you take one class, which is called maybe Sentosas for now, versus Feriscolor and Virginica. So that is how it works. Okay, a separate binary classifier is trained for each class, and final prediction combined result from all other binary classifiers together. So you get the final result. So it's very good in that case. So let's break our metric down. Explain a little bit more about it. You can understand what I'm talking about. We have a predicted class. We have casual class. Here we have not yet labeled our function matrix now. Not labeled for now. We are just at least starting. You can label it actually. Yes, you can label. You can even bring that in a picture in a picture form or image form. Yes, there are many ways you can handle that. But don't worry for now. It's just elementary parts. Okay. So this predicted value and actual values are here. So you can see them here. So positive and negative, positive, negative. So this diagonal one now are positive one. Are the true one true? It's called true positive and the true negative. All right. So this off diagonals are called false. Okay. We have false negative and false positive. So these are called type 1 and type 2 errors. All right. Type 1 error means false positive. Type 2 error means false negative. Okay. So I've explained that in my introduction. Maybe you can check later to see if you remember. Okay, so yes, formulas actually. For sensitivity, we have true positive over TP, which is true positive plus false negative, and so on and so on. So accuracy is just this plus this, okay? This plus this over total of everything, all right? It's as simple as that. You can calculate with your hand, okay? This one plus this one over this plus this plus this plus this. That's what it means. So then we have a true negative value. We have a precision here, which means TP over TP plus FT. So it's as simple as that. Now, what the accuracy means that it means correct prediction of a total prediction. That's what we do. Correct prediction means that they are all true. They are all true, which means they are correct over the total prediction. All right, this is called overall performance. Okay. Then we also say that precision means that the true positives here, which we have gotten here, over true positives plus false negatives, which is this one, which means how reliable positive predictions are. So we show that showing us the reliability of this positive precision we are having now, because all of them are positive. Positive here, positive here. You can see positive, positive, positive. How reliable are they? It's called negative, negative, negative. Okay. Then we also have a recall, which means true positive over true positive plus false negative. The ability to find all positive cases now. Look at the ability to find them, all positive cases. Now we are going to explain more about that maybe as we continue under result and discussion during towards the end. So we have F1 score to multiply by precision score that times recall. Then we have divided by precision plus recall. So this balance measure of precision and recall. So we want to balance between precision and recall. We use F1 score to balance it. Okay, so we also have a ROC curve, which model ability to separate classes into their own different parts. So that's what we have so far. So and it has a score, which I showed just now. So far so good. I think this is just an introduction to machine learning using random forest to show us example. So in the next class, we'll now be starting proper machine learning step by step. So thank you for joining today. I will see you in the next class. You can like and share. If you have anything that you want to say, you can comment in the comment section. I will reply. And if you have anything you are missing, you can also alert us, then we can include. Thank you so much. See you in the next class.